what I'm going to talk about today is revisiting the fundamentals, understanding radionuclide behaviour using 21st century tools. So an overview of what I'm going to talk about today is why do we need to predict radionuclide behaviour? What processes do we need to understand and model? How do we quantify and model those processes? Think about thermodynamic data and compilations of data into databases. Look at uncertainty in that data and what that means for model predictions. We'll ask where that data comes from and think about several experimental techniques that are used to derive this type of data, and then briefly end on thinking about what the future will bring for this topic. So why do we need to predict radionuclide behaviour? The concept of geological disposal of nuclear waste involves isolating that hazardous waste and the hazardous radionuclides within it from the wider environment, from the biosphere. And that's made up of multiple components, from the waste form itself, engineered barrier systems which are designed to contain those hazardous materials, and then retardation of the migration processes through a geological barrier. And to understand and develop a safety case for this disposal concept, we need to be able to predict how different radionuclides will behave under a wide range of conditions. And because the timescales of these processes are so long, many tens, hundreds of thousands of years, we need to be able to extrapolate our knowledge of processes that we can study in the lab under realistic timescales to those longer timescales. So we need to use computer models to help us do that, to help predict what the releases of contaminants into the environment will be. Here's an example of a type of modeling simulation that is used as part of developing a safety case. So this is a hypothetical low and intermediate level waste repository, and you can see the model outputs here are showing activity in becquerels per year versus time for a range of different radionuclides into the biosphere. And these outputs feed into a hierarchy of models that are used in a safety assessment. It's not possible for one model to do everything. We need to start with our kind of fundamental knowledge and data. We need to feed that into detailed mechanistic models of small scale processes and small components of a disposal system that then feed into larger system level models which output safety indicators such as risks or doses to the public. So thinking about radiochemistry, fundamental processes, which ones do we need to model? What is important? First of all, solution speciation. How do these elements behave in solution? What form do they take? Their solubility, so precipitation, dissolution. Here I've shown an example. It's not actually a radionuclide, but it's also really important to consider the non-radioactive species that are present as well. They have a very strong impact on radionuclide behaviour. Surface interactions, absorption, these are some of the processes that control how quickly radionuclides can migrate through different environments and potentially reach the biosphere. So how can we quantify these processes? I've got an example here. This is americium, important actinide, which can form very strong solution complexes with organic ligand called EDTA. And this complex with americium is highly soluble. So this could mean that it would make americium much more mobile in the environment if this reaction was to take place and be dominant. And we can write this process as a chemical reaction, as shown there. And using the theory of chemical equilibrium, we can define an equilibrium constant for this reversible process, as is shown there. And when this is applied to a solution complex forming, this equilibrium constant is also known as a stability constant. So for our EDTA and americium example, we can define an equilibrium constant in this way, with the quantity of the products versus the quantity of the reactants And it turns out that this number for this example is very, very large. It's around 4.7 times 10 to the 19. Because these equilibrium constants vary hugely by tens of orders of magnitude, it's generally easier to give them in a logarithmic form. So here we can express that as a log k of 19.67. And according to our theory of chemical equilibrium, this value is constant across all conditions. And it's an example of thermodynamic data that we can use to predict complex mixtures and complex systems over time. How do we then go on to model these processes? We can use software tools such as FreakC, Geochemist Workbench, that allow us to predict over the behavior over a wide range of conditions. And anyone who knows me knows that I'll take any opportunity to show a FreakC input and output file. So here's a really simple input that we can look at our americium and EDTA example a little bit more. So we can define a solution that contains americium, calcium and carbonate in equilibrium with calcite, EDTA, sodium, and quite a strongly alkaline pH. And if we take a look at the small part of the output of this model, it's done in FreakC using the thermochemie database, we can look at the predicted americium speciation solution, and we can see that the most dominant complex or dominant form is EDTA americium complex that we looked at in the previous slide. But interestingly, only around 56% of the americium is complexed here, even though we saw that the log K for that process was really high. So why is that? If we look at the EDTA speciation in a little bit more detail, we can see that it's actually dominated here by calcium, interaction with calcium. So as well as that thermodynamic data for the two species that we're most interested in, it's also essential to be aware of all the other competing reactions that are taking place. So this system is relatively simple, with a handful of components, but you can see that there are actually dozens of different reactions that can take place. And as well as that log K that we saw on the previous slide, we also need to know the data for every other possible combination that can form as well. So where do we get this data from? We can't just use that one particular equilibrium constant. We need to know many, many more. And we can use thermodynamic databases. Some examples of these, there are many that are out there and freely available. The Nuclear Energy Agency distributes their own database, and they have a very significant ongoing project to review data and compile data. Thermochemie is another commonly used database, which is compiled by a consortium of European waste management organisations, including NWS. And then there are also country-specific databases as well. So an example here is a PSI and NAGRA database for a Swiss disposal case. Now, I won't go through the detail on this slide, but I just wanted to give you an idea of the level of effort and work that's required in compiling these databases. It's very, very significant. So to be able to produce these databases, it requires a huge amount of time and effort to find literature data, experimental data, review that data for quality, fit parameters to derive the equilibrium constants, ensure that the data is self-consistent. A very common issue is correcting for ionic strength, and then a lot of work in integrating that database and properly documenting it as well. So next I wanted to talk a little bit about uncertainty in the data and what that means for our predictions. So I've got another example here of uranium solubility. So under certain conditions, uranium solution solubility could be controlled by a reduced amorphous oxide phase, UO2. And in the thermochemie database, there's an entry for that phase. Give the reaction for its formation is given there. And as well as the text file, which the database normally takes the form of, thermochemie has a website where you can look in more detail about the underlying data that's present for each of these processes. So if you look on the website for this this uranium phase, we can see the log K for that reaction. And we can also see an uncertainty value. In this case, the log K is quoted as -1.5 plus or -1. So this is a bit of an extreme case. The uncertainty value generally is not this large, but what it means is for this process, the log K is actually between -2.5 and -5. So what does that mean for the solubility of this UO2 phase? If we use freq-C again to simulate the solubility of uranium, you first of all using the baseline or best estimate value, we get this. And then if we look at the extremes, the outer edges of the uncertainty, we can see that the solubility actually spans 2 orders of magnitude. So it could range from between around 3 times 10 to the minus 10 to 3 times 10 to the minus 8 moles per litre in solution. And that could have quite significant implications for the source term in a reactive transport model, the risk calculated for a safety case, and it really shows why understanding uncertainty in these data is important and why high quality data is essential. So next I'm going to talk about where this data comes from, and in a short talk like this it's not possible to give a comprehensive overview of techniques, but I've chosen a couple of selections, 2 methods that are more traditional and have been used for much longer periods, and then 2 that are more modern techniques. So some of the oldest techniques to derive these kinds of data include titrations, so the careful mixing of solutions and monitoring of changes, one of which is monitoring the pH, so it's potentiometric titration, when two solutions are mixed together. And these produce quite distinctive titration curves that can look like this drawing in the middle here. And the way that we can derive thermodynamic data from these titration curves is by using some speciation software that allows us to fit data to our fit model data to our experimental data. So we need to have some understanding of the system already. We need to be able to propose a speciation model, so metal with a certain number of ligands, and we also need to have an initial guess for our equilibrium constants. And what this speciation software allows us to do is calculate theoretical titration curves, and then we can vary those constants to be able to get a closer fit as possible. And that's what's shown in the image there. And this is how potentiometric titration is used to derive log K values for certain processes. Another more traditional technique is spectrometry. Example is UV-vis spectroscopy, relatively simple technique. It measures the absorbance of light by solution species at specific wavelengths due to electron transitions. And it's applicable to many systems as long as they absorb in the UV visible range. I've got some literature data here that we can see. So on the left, I've got some absorbance spectra for uranyl sulfate systems. So what has been done here is, first of all, a spectrum measured for uranyl on its own, and then different amounts of sulfate added as a ligand, as a complexing ligand. And as those ratios change, you can see a change in the spectra. That allows deconvolution of the spectra to show the individual contributions from specific solution species. And then again, a fitting process can then be done to derive equilibrium constants here using specific wavelengths. So these traditional techniques do require some existing knowledge of the system. We need to have an idea of what the important complexes are before we start this process, and some estimate of the log K value. So it can't just go in completely blind and get useful data out of it. Looking at more modern techniques and the rise of spectroscopy over the last several decades, an example is time-resolved laser-induced fluorescence spectroscopy, TRLFS. This method uses the emission of light. So rather than the absorbance, we're measuring the emission of light that occurs when certain elements relax after being excited. And this emission or luminescence is highly element specific, very sensitive, and that makes it ideal for looking at trace, ultra trace concentrations, and many actinides and lanthanides are suitable for study under using this method as shown there. So a short laser pulse excites the species, which then causes the emission or fluorescence. And importantly, that fluorescence doesn't occur instantaneously, but over a period of time, which gives a distinctive lifetime for a particular species. And that allows, again, the deconvolution of overlapping signals in a spectrum. So shown here is a TRLF facility at UKNNL's central laboratory. And if you look closely on the screen, you can see a distinctive spectrum for americium fluorescence. And the image slightly to the right there shows a bit of a close-up of the laser entering the chamber and the cuvette there where the sample is contained. So we're currently developing the system at the moment to be more sensitive for americium study at very, very low concentrations at high pH values. Here's some literature data from a recent PhD project at the University of Manchester, Laura Lopez Odriozola, and she studied uranium interaction with gibbsite and cement phases. So this technique is also good for looking at the properties of elements that are absorbed or attached to the surfaces of materials as well as solution species. So she was able to use this method to understand the binding mechanism of uranium onto these solid phases using TRLFS at the university. Some more advanced spectroscopy techniques include X-ray absorption spectroscopy. So now this is a technique that requires a laser, an X-ray synchrotron. So not something that can just be done at a university. The image shown here is from the Diamond Light Source, UK's synchrotron. And this method uses the absorption of X-rays to study specific elements. And there are various modes of that, including XANES, XAFs, that probe different regions of energy in an X-ray absorption spectra that can give information on coordination environment, bond lengths, and that provides a real critical supporting role in understanding the detailed structure of complex solution species or species that are attached to solid surfaces as well. This does require a larger concentration than some other methods, typically in the ppm range. And then the chart here shows the characteristic edges of an absorption spectrum and how they link to the core electronic structure of these elements. So it's core electrons that are being excited by these X-ray absorbances. Again, this does require some fitting and interpretation to be able to interpret that and understand what that means in terms of bond lengths, numbers of neighbours, and interpret that in the context of what's expected. So again, some prior knowledge of the system is needed to be able to fully interpret that data. I wanted to include a quote here that I found in a NEA publication. So this is the Nuclear Energy Agency from 2003. So this was kind of around when data from some of these advanced spectroscopy methods were starting to come into the wider literature and be used to derive thermodynamic data and understand structures. And they found that the spectral resolution of these techniques is often much better than traditional methods, such as spectrophotometry. But importantly, the data that is being obtained by these new methods in general agrees very well with data obtained by the more traditional methods. I think that's quite an important thing to remember. The older, more traditional techniques, there's not necessarily anything inherently wrong with them. They're not necessarily obsolete and need redoing using these more modern methods. These modern methods are more complementary. They allow us to study a wider range of systems and more challenging conditions, for example, where the concentration of solution species might be much, much lower. So starting to think about what the future will bring. There are constantly improvements to experimental methods, including spectroscopy, so enhanced sensitivity and spatial resolution. It's increasingly possible to study dynamic systems in situ and also combine techniques to study systems using multiple techniques. Improvements to sample handling means that we can reduce the volumes and radiological risks associated with analysis. And computing power is always improving and helping manage the large amounts of data that can be generated using some of these methods. There's also some advanced X-ray techniques that are ongoing at the moment, that are available and becoming increasingly available to researchers that can give us even more detailed information compared to EXAFS and ZAMES. And also ways of combining redox control with this spectroscopy as well can help study redox sensitive elements in much greater detail. And in the UK, the diamond light sources will be, over the next several years, receiving some upgrades that will provide improvements to brightness and coherence. That will improve resolution, faster data collection, and provide greater opportunity to use some of these new X-ray capabilities that I've mentioned. This one is a bit of a left field future potential technique. So quantum chemistry, could we predict this thermodynamic data from first principles? Could we do away with experiments altogether? I don't think so, but there are rapid developments being made in these quantum chemical methods using density functional theory, for example, and already they do allow us to make accurate predictions of actinide complexes and structures, often actually more detailed than from some experimental techniques. You can also use this method to predict reaction energies and log K values, but at the moment these methods are not good enough to compete with experimental data. A real hurdle and limitation is that a lot of these reactions are driven by the entropy of water molecules that are involved as a solvent, and the simulation of many water molecules interacting with one another is very computationally difficult. So at the moment, that is a real hurdle to these techniques in predicting the data from scratch. What about machine learning and AI? Machine learning is already being used to help process very large amounts of data and find trends and correlations that might be difficult by humans or more traditional techniques. And I think the jury's out on how AI might help us with some of these techniques in the future, but definitely something to keep an eye on, I think. So just to sum up, thermodynamic data are really important. They underpin our predictions of radionuclide fate and support the disposal system safety case. Uncertainty can have consequences in these calculations. So errors or uncertainties can lead to quite big differences in model outputs. In compiling databases, we start with work in the lab. We do experiments. We combine the data with conceptual models, and then we're able to fit constants that then can be used in predictive tools and models. Spectroscopy over the last 20 years or more has been changing the game. It's given us much more insight into structure, speciation, and behavior, and we can study much more difficult conditions than was possible before. And innovation is continuing as well. New tools and theory will continue to reduce uncertainty and strengthen confidence in our predictions and underpinning of environmental safety cases. Thank you very much.